If this represents the path of an object moving under the influence of an inverse square force that's radial in nature, meaning that the force is radially directed back toward the origin at every point and inversely proportional to the square of the distance of the point from the origin, then we've seen that the quantity dA dt is constant, and that's r squared d theta dt, and that is constant, meaning if I take r of t here and r of t plus delta t, and then let's say we take r of t plus 2 delta t. Now this isn't a very good picture because actually since r gets bigger here, then since this appears to have a slightly bigger angular increment, this picture is not going to be correct, as we'll see. The region here has area approximately equal to r squared times d theta dt times delta t, and this has area approximately equal to r squared d theta dt times delta t. If the delta t's are the same, then the rate of change of the area is constant, so that the areas will have equal changes. So if delta t is uniform, that is, we have the same delta t between this point and this point as between this point and this point, then these areas should be the same. And this argument could be made more rigorous and extended to show that in equal time intervals, the area swept out by the r vector, and that would be the area of the region defined by the two r vectors and bounded by the curve. That area is going to be the same as long as time intervals are equal. Now we could develop that in terms of the integral. I'm not going to go into that detail at this point, but that's the ultimate meaning of this result, that as applied to planets, the path of a planet sweeps out equal areas of the region in equal times.